We're going to talk now about something called polynomial functions, which once again, like we did in Unit 1, like we did in Unit 2, eventually we're going to get to the point of graphing them. And if you're given their graphs, finding the equations of them, okay? Because those things are where the applications take place. But first, we've got to do some work on what exactly these things are. And then we've got to work on a little bit of math that's going to involve some factoring and some division that's going to help us graph these things and help us find the equation of them given their graphs. So a polynomial function looks like this. Now, don't get thrown by this. It looks very mathy. But basically, a polynomial function, it's got numbers and variables in it, and adding and subtracting, so it's got terms in it, 1 to however many number of terms. And what makes it polynomial is the numbers in front of the variables, or the coefficients, have to be real numbers, which is essentially, for your purposes, any number. And the exponents have to be whole numbers. We can't have negative exponents or any fractions. Okay? So something like this. If I had, 5x to the 4 plus 3x to the third minus 1/2 x squared plus x minus 7, that would be a polynomial function. Okay? Because all the numbers in front of the coefficients are real numbers. Okay? And if you look at all the exponents, there's no negative exponents, there's no fraction exponents. That's really what it comes down to. Okay? So it says here, and the exponents must be a non-negative integer. So like 0, 1, 2, 3, 4, etc. And like I said, the coefficients, they're real numbers. What's a real number? A real number is any number that can be written as a fraction, or any number that can't be written as a fraction. So like any whole number is a real number, because you can write any whole number as a fraction, like 7 is the same as 7 over 1. Okay? They can also be negative, like negative 10 is a real number because it can be written as negative 10 over 1. All fractions are obviously real numbers because they're fractions. They can be written as fractions. All decimals are real numbers because they can be written as fractions. Even those ones that can't be written as fractions, decimals that never end or never repeat. Can you think of a number that never ends or never repeats that you've encountered? Pi. That's a real number. We can't write it as a fraction, but it's still a real number. Okay, some other words you need to be familiar with polynomial functions. The degree. Essentially, the degree is the highest number used, the highest exponent you see. So when I look at this example, the degree is 4, because that's the highest exponent I see. The leading coefficient. That is the coefficient of the term that contains the highest exponent. So the leading coefficient, well, this is the term that contains the highest exponent. The leading coefficient would be 5. That's it. And the term that doesn't contain a variable, even though we could write it using a variable, is called the constant. So in this example that I wrote here, the constant would be -7. You don't have to worry about defining these, but you do have to worry, you do have to be concerned about if I say, give you one of these and say, Tell me the degree. Tell me the leading coefficient. Tell me the constant. Tell me whether it's a polynomial function or not. Okay, and then we'll look at other properties a little bit later on. So just as an example, we've got 6 functions here, or what I believe to be functions, and we have to determine whether they're polynomial or not. And if they are polynomial, you are asked to state the degree, the leading coefficient, and the constant in each. So the first one, what do you think? Why are you shaking your head? No. Or are you shaking your head no because you're just fed on it? No clue what you just said. Hey, you're talking like Ava. Ooh, took a shot at her and she didn't even do anything. What's that?
Skip me.
Okay. Yes, no? What do you think?
I have a question.
Okay.
For the constant, does it have no variables on numbers?
Yes. Remember what I said about the exponents? They have to be whole numbers. 0, 1, 2, 3, 4. Is that what this is? No. No. Because it's not a variable exponent. We can't have that. So we stop there. We can't name anything in it because it's not a polynomial function. How about the next one? What do you think? Look at the exponents. Are they all whole numbers? Yes. So we can then state the degree, and I'll just put LC for leading coefficient, and constant. What's the degree? 15. What's the leading coefficient now that you know the degree? 3. It's the number in front of the term that contains 15. What's the constant? Negative 17. Next one. Yes, no? Look at the exponents. Remember what I said? The exponents have to be, yeah, they have to be whole numbers. They can't be negative. No, because we have a negative exponent. Next one is a little challenging. What might throw you off in this question as to determine whether it is polynomial or not? The square root. Do you remember how to write square roots as exponents? If I take the square root of something, we learned this in grade 10. I know that's a while ago. It's the same as raising it to the, sorry, 1/2. If you remember, square root, actually, there's a little 2 in front there. And then when we change these to fraction exponents, the root becomes the denominator, and whatever we raise it to becomes the numerator. So like the square root of x is x to the 1/2. The cube root of x is x to the 1/3. Okay? So right away, no. Because it's not a fraction exponent, we can't have fraction exponents. How about the next one? Yes. What might throw you off here is the pi, but remember, the coefficients, as long as they're real numbers, okay, we're okay. So what's the degree? 5. What's the leading coefficient? Pi. And what's the constant? 7. Good. This last one is kind of a special case because you can write, like, you might look at this and say, well, there is no exponent. So because of that, it's not a polynomial function. But we can actually write any number with a variable and an exponent. I can attach an x here, but what do I have to raise it to so that this whole thing stays as 9? 0. Because remember, x to the 0 is 1. And 9 times 1 is just 9. So we can write any constant technically as a term with a variable and an exponent, which means it is polynomial. It is. Sorry, this is yes too. And all the answers for degree, leading coefficient, and constant are all within that one term. What's the degree? 0. What's the leading coefficient? 9. And what's the constant? It's also 9. Okay. Okay, so now we know what these things are and what they are not. Let's talk about properties of polynomial functions that we look at. And these are some of their properties. We've already looked at degree. End behavior, we haven't really looked at with any functions yet that we've studied. Domain and range, we've done with other functions. X-intercepts, in this case, the number of x-intercepts we've done, as well as the y-intercept. Okay. Basically, what these things look like are parabolas that are connected. So like this is a polynomial function. Think of it like two parabolas connected. This is a polynomial function. Think of it like 3 connected. And I can keep doing that. I could go upside down like this, because the parabolas could be upside down. So all of those are polynomial functions. And when we talk about their end behavior, we talk about what's happening at the ends of the graph. Okay? And two things are happening. Either they're going up into a certain quadrant, if we graph them, or they're going down. Okay? There's no other way. I mean, we can't have one that looks like this. Okay? So, if it is an odd degree, which means the highest exponent is 1, 3, 5, 7, 9, etc., it's going to look like this, where the ends go in opposite directions. If it's even degree, 2, 4, 6, 8, etc., the ends are going to go in the same direction, up or down. Okay? Because if you think about it, you already know two types of functions. That's a line. What's the equation of that function? It's y equals x plus something, or y equals x minus something, or y equals negative x. There's no exponent on the x. Well, there is. It's a 1, but we just don't write it. Okay? That's an odd degree, which means that the ends go in opposite directions. Last year we did parabolas, right side up and upside down. Well, those all had degree 2, x squared. Their ends went in the same direction. We're just extending that to some funkier looking graphs. Okay. Another thing about the x-intercepts, okay? If we've got a polynomial function that has degree n, the highest exponents, that's the maximum number of x-intercepts will be. Okay? So if we have a function of degree 5, it's going to look like this, and it's going to have a maximum of 5 x-intercepts. It might have less, but it can't have more. Okay? All right, let's look at the ones that we're going to focus on. First two, actually first three, are review. We've done these, okay? I mean, these were done in middle school in grade 9. Same with these and grade 10. These were done in grade 11. And now we're just going to extend it to a few more types. So degree 0, we call a constant function. Okay? Should I get the? It is even degree because 0 is considered an even number. What's the maximum number of x-intercepts? 0. We can't have any x-intercepts because a constant function is a horizontal line. It will never cross the x-axis. Okay, so it has 0. So in this example, this is y, or f of x, equals 3. What's happening on the ends? Well, we're just extending horizontally. Going in, they're not really going, well, I guess they are going in opposite directions, but we don't really apply that to constant functions. What's the domain? Negative infinity to positive infinity. Goes to the left forever, to the right forever. What's the range of this one? Just 3. And remember, if you're writing a single number, that's where you have to use the braces. How many x-intercepts? Does it cross the x-axis? So 0. What's the y-intercept? 3. Okay. Okay, what happens if we have a function of degree 1? Well, that is always a line, so we call it a linear function. And since it's degree 1, that means it's an odd degree. And how many x-intercepts? 1. Okay. Slanted line will always cross the x-axis, but it'll only cross it once. Well, what's this specific example? Remember, I could use y or f of x, so I'm going to just switch it out. In this one, this is the equation f of x equals x plus 1. Now, for the end behavior with these ones, this is how we say. First of all, look at the left side. It extends down into which quadrant? 3. And then on the other side, the right side, in this case, it extends up into quadrant 1. So that's how we talk about the end behavior. Is it going up or down, and which quadrant? What's the domain of this one? Sorry? Goes to the left forever and right forever. What's the range, lowest to highest?
Same thing.
That's true for any line, as long as it's not a constant one. Okay? They go up, down forever, left, right forever. In this one, there's one x-intercept, yes. Looks like it's at about a half. And what is specifically the y-intercept? 1. Okay, again, we've done these. We've done this, degree 2. We did these last year. What kind of functions did we call these? Quadratic.
And since they are all x squareds, they are even degree.
Now here for the x-intercepts,
There's 3 possibilities. We could have 0, 1, or 2.
but we can't have more than 2.
Because if you think about it, we could graph another parabola like this, over here.
No x-intercepts.
Okay, so therefore that fits. We could draw one that looks like that, where it hits the x-axis once. Or this one hits the x-axis twice. That's
This specific parabola is given by the equation y equals x squared minus 3, because we take x squared and move down 3. What's the end behavior? What's happening on the ends of this one?
both going up. So extends up in which quadrants? 2 and 1.
What's the domain of this one?
Negative infinity to positive infinity.
Once again. But the range of this one is not everything. It's what?
-3 to positive infinity.
How many x-intercepts does this one have? 2. And what is the y-intercept of this one?
-3. Okay, now we get to the newer ones. So this one, degree 3. Think of it as made up like of 2 parabolas.
Okay. Any idea what we would call it? Cubic.
Remember when we find the volume of 3 dimensions,
We do units cubed.
since the degree is 3, that is an odd number, so it is an odd degree.
The number of x-intercepts.
Well, it is possible to draw one where there's only 1. It is possible to draw one where there is 2. And in the one I've given you, there's 3.
So that's a possibility.
So like here's 1. Sorry. Yeah, here's 1. And then if I did 2, I would just go like this. Okay, so they are possible to draw.
This specific example is
Y equals x cubed plus 2x squared minus x minus 2.
So we are going to get to the point where I give you this and you will graph this. Or I give you this and you will tell me this. Okay, that's sort of the ultimate goal. What's the end behavior? Name the point. Like I usually go, okay, what's happening on the left side? What's happening on the right side? Down quadrant 3, up quadrant 1, extends down quadrant 3, up quadrant 1. The domain of this one, furthest left to furthest right? Yeah, negative infinity to positive infinity. The range of this one? I'm just going to pretend I heard that. Negative infinity to positive infinity. How many x-intercepts does this one have? 3. What's the y-intercept? -2. Degree 4, which is an even degree. Any idea what we call that? Think French for 4. Yeah. Along that line, quartic. How many x-intercepts does this have? Well, with even ones, it's possible to draw them with 0. I could draw one of these that only has 1, or 2, or 3, or 4, which this specific one has. But if I took this W shape and move it above the x-axis, it has 0. If I took one of the ends and put it on the x-axis, it has 1, and so on. So it is possible to draw this specific example is f of x. Remember, I can use them interchangeably. X to the 4th minus 5x squared plus 4. What's the end behavior of this one? Extends up. Quadrant 2, quadrant 1. Domain. Negative infinity to positive infinity. Again, it seems that all of these, the domain is not going to change. However, the range does change when it's an even degree. What's this one? It is about, we're going to, yeah, negative 2.2, we'll say, to infinity. And nice to have one that bottomed out at -2, but that's kind of hard to create. How many x-intercepts does this one have? And what is the y-intercept of this one? It is also 4. The last one is degree 5. We're really not going to go higher than this because this is starting to get pretty crazy. Obviously, because it's degree 5, it's an odd degree. Any idea? It's actually based on the number 15 in French. Quintic.
This one, it has to have at least one.
Odd degrees can't have zero. They have to go through at least once.
It could have 2, 3, 4, or 5,
But it can't have more than its degree.
this specific one is the equation y equals x to the 5th minus 5x cubed plus 4x.
What's the end behavior?
Extends down in quadrant 3, up in quadrant 1,
Domain,
everything, negative infinity to positive infinity,
range,
negative infinity to positive infinity. Notice that the domain and range of
odd ones, odd degree, are always negative to infinity to positive infinity. How many x-intercepts does this one have?
it's got 5, and what's its
X-intercept?
0.
Okay, that was a lot.
But we're getting there. Okay. One other thing I want to talk about.
We don't have to do a lot of writing here. What happens if there is a negative with the leading coefficient?
Well, we saw last year with grade 11 that if we had a quadratic function that had an x squared in it, it was going to look like that. But if it had a negative x squared, it was going to flip upside down.
The same idea applies to any polynomial function. So like here, x to the 4th, the end behavior, both ends are going up. Okay? But as soon as I put a negative in front of the degree, the highest exponent, it flips upside down and it extends down into each quadrant on each end. Okay? Don't worry about this y equals x stuff. I'm not going to address that. So here's an example of a cubic function. So notice that if it's positive, okay, it goes down to the left, up to the right. But as soon as I put a negative in front of that x cubed, it flips. It goes up to the left and down to the right. One way you can always sort of remember this, think of the right side. Okay? If it's positive, the right side will always go up. Doesn't matter whether it's odd or even. Okay? But on the left side, it will go up if it's even and positive. Okay? But it will go down if it's even and negative. So think of the right side. Maybe that's how you want to sketch.
So if I had something like negative x to the 5th,
well, positive x to the 5th, I know goes up to the right.
so that means negative x to the 5th must go down to the right. And then I just draw my x to the 5th function.
So that's what it would look like.
Because it has to go in opposite directions.
And that's really all I wanted to say on this page.
So let's just here look at a couple of examples.
And what you could be asked. So we've got two functions. You were asked to list the following: what kind of function it is, whether it's odd or even, the end behavior of what the graph would look like, how many possible x-intercepts it could have, you don't have to be precise, and what the y-intercept is.
So for this one, x to the fourth plus x cubed, etc. What type of function? What's the name we give it? Quartic. And odd or even? Even. So because it's even, and because it's positive in front of the x to the fourth term, what's the end behavior? Up in both. Okay? So extends up Q2 and Q1. How many possible x-intercepts could it have? Sorry, I should say the maximum number of x-intercepts. 4? Yes. Max 4 x-intercepts. And then for this last one, we just got to do a little bit of math. To find the y-intercept, what do? We make x equals 0. So if I make all the x's 0 and calculate this, what does the y-intercept become? 3. You try the second one. Just so you can get a handle. Right? Quintic? Odd even? Odd. And behavior. Sounds like we have some arguments here. It's flipped. Remember, odd ones always go like this on the ends. So now they're going to go like this. So it extends up in quadrant 2, down in quadrant 4.
Once we finish all these functions, there's a dance you can do to model them all, but you think I'm going to be showing you the dance? No.
Maybe I'll show you a video of it. What's the maximum number of x-intercepts? 5. Y-intercept? 0. Good.